So what's a neural network? PyTorch has a simple explanation that says that neural networks are a stack of layers and modules that perform operations on data. So let's take a look at this simple neural network. It has three layers: an input layer, a hidden layer, and an output layer. The input layer is the data that we're feeding into the network. The hidden layer is the layer that does the actual computation, and the output layer is the result of this computation. Now there are 5 nodes in the input layer, 3 nodes in the hidden layer, and 3 nodes in the output layer. The nodes in the hidden layer are connected to all of the nodes in the input layer, and the nodes in the output layer are connected to all of the nodes in the hidden layer. This is also referred to as a fully connected network. Now shortly you'll see how this is done with PyTorch, but for now let's focus on the first neuron in the hidden layer. Now the first neuron in the hidden layer is connected to the first, the second, third, fourth, and fifth nodes in the input layer. Let's take a look at the computation that happens in this first neuron in the hidden layer. So I'm going to put in some random numbers in here. And if you just look at the first neuron in the hidden layer, you see that it has 5 different weights as well. So there's the 0.5, negative 0.2, negative 0.3, 0.1, 0.2. These weights, we also call them the parameters of the network. And notice in here that the weights might be a negative number. So in this case here, 0.2, negative, 0.3, it's negative. And what we do next is we are doing a weighted sum of the input data. The weights are, each of them are multiplied by the input data, so the corresponding input data, and then they're added together. So 0.5 multiplied by 3, 0.2 multiplied by 2, and 0.3 negative multiplied by 3, 0.1 multiplied by 1, 0.2 multiplied by 2. When you hear people say that they're training a neural network, you're actually training the weights, right? So when we say that we're training a neural network, we're training the weights, and we're trying to find the best weights that will give us the best output, or in other words, the least error. So we're trying to do this, and we do this for all of the different neurons, and we do that for all of the different neurons in here as well. In PyTorch, this operation is done with a linear layer. The linear layer takes in the input data and the weights and return the output. But this is not all. This is 0.7, but what we do, the result of this weighted sum is also added with a bias. So there is a bias here, added to a bias. Now the bias is a constant that is added to the weighted sum. You can think of them as the constant term. Sometimes you hear the word bias term, sometimes you hear the word constant term. Now this bias is also a parameter of the network, which means we're also interested in finding the best value for the bias. So all of these numbers are all randomly initialized, or they set up to be 0, and then what you do is through this backpropagation and feed forward and backpropagation, you're going to find the best estimates of this value, the estimates that give you the least error. So of course we want to repeat the process. We bring the 0.7 and we plus 0.5, that's 1.2, we bring that down, and we follow, we continue on the process. So each one of the weights, each one of the input, and do that for all of the input neurons. And as you do it for the second and third neuron in the hidden layer, you want to notice that the introduction of the bias terms here means that there is a, instead of having only 5 terms, you're actually having six different weights. Instead of having 5 different weights, you're having 6 different weights. So 6 different coefficients, and that this bias, also notice that it has the potential to change a non-positive number to a positive number. So a neuron that otherwise would have been non-activated can now be activated, and the same goes the other way, so vice versa. Suppose without a bias coefficient of 0.5, the third hidden neuron would have been non-activated, because it would have been, let's say, negative 0.1 in this case, right? But with a bias coefficient of 0.5, because you have to add the 0.5, it takes it from negative territory into a 0.4 territory. So these two are activated because they're both above the threshold, and in this case, the threshold is 0. The ReLU activation function, short for rectified linear unit, is a function that takes in a number, so takes in x, and returns a number, returns an output of x as well. If the number is positive, it just returns the number. If the number is negative, it returns 0. This is a very simple function, but it's very useful as it introduces non-linearity to the network, allowing the network to learn more complex function. So in this case here, 1.2, is that greater than 0? It is, so it's going to keep 1.2. 0.4 is greater than 0, so it's going to keep 0.4. But the earlier value, which is 0.8, negative 0.8, that's a negative value. So you take the maximum between 0 and negative 0.8, and so that would be 0. And finally, we talk about the output layer. So you want to perform the same operation, do the same thing as what you've learned there. And now you have, let's say, 3 random values, 0.4, 2.9, and 0.2. Notice that the output layer is also a linear layer, and it takes in the output of the hidden layer and the corresponding weights along with a bias. It has its own bias here, right? And the results of this is not bounded by any range. So you see 0.4, you see 2.9. This is greater than the range of 1, for example, right? So suppose you want to predict if this photo contains pictures of my beautiful wife or pictures of any other random strangers, then we can't use this output as is. So what we need to do is to convert this output to a probability. So we do that through a softmax function. And the softmax function takes in a vector of numbers and returns a vector of numbers. So it takes this number and it transforms that to 0.11, 2.9 transform that to 0.83. How does it do that? Oh, that's actually really simple. And the way it does that is it sums up all of the numbers, so 0.4 plus 2.9 plus 2, and that would give you 3.5. And then it takes each of the number and divide by that sum, right? So 0.4 divided by 3.5. Where did 3.5 come from? It's 2.9 plus 0.4 plus 0.2. And then the same thing, 2.9 out of 3.5, that's 0.83, and 0.2 out of 3.5, that's 0.05. So in this case here, it says it's 0.83, and that turns out to be a picture of my beautiful wife. And so that's kind of how you complete a feed-forward cycle. So if you're sweating right now, don't worry, PyTorch actually makes this quite easy for us. So let's take a look at how we could take the earlier neural network architecture and put it together with PyTorch sequential API. So at the very top, we have the import. So we have the import torch, we have import from torch import NN, that's neural network. So neural network.module, we're creating our own class called a neural network. And what we do is we actually subclass. So nn.module, we subclass from that, inheriting some of the functionalities that it provides for us. And we define our own initialization. So first, also inherit whatever it is from the NN module, initialize that, and then we flatten all of this. We spoke about this in earlier lessons. So if you have, say, an image of 28 times 28, you want to take 28 times 28, you want to flatten off that so that it becomes just a one layer instead of having two dimensions, right? Then what we do is we define this using sequential. This is a sequential container, and modules will be added to it in the order they are passed in the constructor. So this matters, right? So we want to first create linear because this is sequential. This is a sequential container. So we want to first create a 5 tree, and then we pass in a relu, we pass in a linear. This will mimic the architecture that we see earlier in the earlier slides. So we have the 5 tree. That's the 5 is the input, 3 is the hidden layer. So this will take from 5 and output to another layer with 3 neurons. Then this will do the same thing. We'll take 3 input neurons, which is the hidden layer, and output to 3 output layer. And then we want to find the neuron that has the biggest, out of all the 3 output neurons, we want to find the one that has the biggest probability. And if that turns out to be the biggest probability, then we say, okay, that's the image of my wife. So what we have now is just a stack, a linear value stack, and we need to, at a bare minimum, we need to have a method to tell this neural network how to perform the feed forward operation. So this is a forward pass, or forward, we call it a forward pass. So it will basically take a set of data, it will flatten it out. So instead of 28, 28, you have the two of them multiply, 784, and then take that and you perform the linear value stack. Where is this defined? It's here, right? This is where it's defined, linear value stack. And it says, well, perform on that, and then you would get a set of logits. This is the logistic regression if you learn about that. But this is still not probabilities. You want to take logits and you want to convert that to probabilities, all right? So what we have in the following code is we basically take that and we convert them into probabilities, and that's kind of just using the same technique that we spoke about before, which is to take the sum of the vector, and then you take each value divided by that sum, all right? So let's clear all of this, quit it out. I'm going to save this. Notice that I'm just creating some random numbers in here, right? X is just a set of random numbers with a shape of 1, 5. So let's run all of that, and then we'll see, we explain that as we go, right? So first of all, we did print the neural network. So we print the model, and this is kind of how, this is what it shows. It says, first I'm going to take the input, and I'm going to flatten that. I'm going to flatten all of that so that the n dimension is just 1. Then what happened next? What happened is I'm going to create the linear. This is a sequential container. So in there, the first layer would be a linear layer, and the linear layer would have takes in 5 input neuron and then output 3, and that goes into the hidden layer, right? And do you want a bias term? We said bias equals to true. That's the default. If you want to turn it off, you say no. But as I explained earlier, why you would want that, and so we keep that in there as bias equals to true. Then we perform a relu. This has the potential to change a non-activated neuron to an activated one, and vice versa, remember? And then finally we have the linear again, and this one takes 3 and then output 3 as well, and again there's a bias term, all right? So we have that. Now let's take a look at x. How do we get x? We get x by calling a random torch.rand, and then we say we want 5 of them, so we have 1, 2, 3, 4, 5. And what we do is we call model on it. Where do we get model? Model is an instance of the neural network that we created, which is right up here. So which is between line 4 to line 18. There's only 14 lines of code to create one. Okay, so let's go ahead and take a look at logits, right? So this is logits. So it turns out the biggest probability would be the last class here, right? The last neuron. So we do pred probability. So this is basically the softmax function, and now we have the output, right? And we see that if we take the sum of this, right, we call sum on it, you will see that this all becomes, they sum up to 1. So this can be treated as probabilities. So we treat them as probabilities. If you learn any kind of logistic regression in the past, you may still recall that lesson. So we convert the log of odds into probabilities in here. And now we find, okay, so is this is this a sneaker, is this shoes, is this a hat, is this a cat, a dog, or a raccoon? And you take the one with the maximum. So to take the one that is maximum, you could just find the maximum. You could say argmax, and that would just give you whichever one is the maximum. Sorry for the dot sum, you don't want the dot sum, you want to find the maximum, which is this. And it's going to tell you that the tensor at the index number 2. So this is the one with the maximum, and this is the class it's going to predict, right? So let's quit it out. And that's kind of how a neural network is constructed. This is kind of the syntax. And so what we want to do now is to take this idea and apply that onto our fashion MNIST dataset and maybe flesh it out a bit. So this is very trivial. It's 5333. What I want to do is want to talk a little bit more about how do you visualize this in the subsequent lesson.